Hi, everybody. I hope that your weekend was productive and relaxing. I unfortunately did not get as much done this weekend as I had hoped, so you probably noticed that we have this lab lecture tomorrow and there isn't a lab online. I've mostly finished it. I'm going to do the finishing touches. I will have that posted tonight for tomorrow's lecture, so you'll be able to get it at some point tomorrow before we attend. Other upcoming things, quiz number 4 is due Thursday. Make sure that you do that by the deadline so that I can put the grading protocol through and then release all the answers. That way you can study stuff. The quiz for Chapter 5 will be after exam number 1 because I don't think we're going to finish Chapter 5 today. But do note that exam number 1 is upcoming. It is on Monday next week. We'll talk more about that in the next lecture, about what that's going to entail and how that works. Other than that, I believe we're all caught up. Alright, so I'm going to do that. Oops. I didn't mean to actually click. There. Last week, we talked about how to make very simple molecules and how to draw the Lewis structure of something like, say, water, CO2, what else do we do? O2, Cl2, things like that. What I'm going to give you now is a sort of 5-step blueprint that will help you determine the Lewis structure for any molecule that I give to you in this class. Excuse me. Just spent like the last hour and a half talking. I was in a meeting. And so the way that we're going to do this is I'm going to first give you the rules. And then we're going to do a molecule, and then we're going to go back over the rules and use the rules to make that molecule. And then from that point on, you have to make sure that every time you draw the Lewis structure or something, you're following the rules in the order that they're written. Because if you go out of order, you'll get the wrong Lewis structure, and that's no good. Alright, so here's the 5-step plan on how to create a Lewis structure for any molecule without doing the connect the dots thing that we were doing last week. Oops, I just saw something back here. Did this not start at 5? It should have. Did something... Is there an error or something on someone's end? Did I not hit a button? It says that I'm streaming. Oh, I see. Oh, that is an issue. Okay, so the title is wrong. I didn't edit the title, so hold on. Tuesday, week 5. There we go. So now what you should do... Sorry about that. I always feel like I miss one thing when I'm doing this, and I do my little checklist, and sometimes I mess up. It should fix that automatically. If it does not, press F5 on your keyboard. That will refresh the page. And the title should change, and everything should be correct. But yeah, it is... Sorry, I was looking on my stream, and I was like, I did change that, right? Yeah, that one works, so... This, where is that? This one right here. That was the one I was looking for. Okay. Alright, let's talk about how to make a Lewis structure. So the first thing that we're going to do is I'm going to give you some molecule. And the molecule that we're going to use in a second is CO2. So let me just write that down here. In this molecule is some number of valence electrons. What we're going to do is we're going to count them all. And the way that you count valence electrons is like you would count valence electrons for anything. How many valence electrons does carbon have? Well, since it's in group 4A, it would have 4 valence electrons. How many valence electrons would oxygen have? Well, it's in group 6A, so it has 6 valence electrons. You just do that for all your atoms. Once you're done, you sum them all together, and you keep that number for now. That's the first step. Step 2 is going to be to draw what we're going to call a framework, or maybe you could call it like a skeleton, or something like that. The way that you're going to create your framework is that you're going to arrange your atoms in a way that you can connect them all together as they should be structured. Now, there are some caveats for that, and those caveats are written in the formulas. So, when you look at the formula of something, if H comes first, then the second letter is going to be the atom that goes in the center. So this right here will be my central atom. And this right here in CO3 2-, the letter that's first will be the central atom. Now, this is going to use a property that we haven't actually discussed yet. It's called electronegativity, and we're going to get to that later today. But what we're doing is we're trying to put the most positive atom first. When we draw Lewis structures for molecules that are molecular compounds and covalent, they don't have any metals in them. They only have nonmetals. But of the two nonmetals that we're considering, one of them is going to be the more metal-like, which we discussed in Chapter 3 and 4. Which element is furthest to the left on the periodic table? That's going to be the more metal-like. That element is going to want to give up its electrons more than the others, and so it will go in the center. So if you're ever given a formula, you're like, what element goes in the middle of my drawing? The element you're going to put down is always going to be the first element listed, unless it's H. H will never go in the middle. You can just skip it. In that case, use the second element. So for our framework right here, since we have CO2, what we would do is we'd do something like this. I'd say, okay, C came first, so I'm going to put it in the middle, and I'm going to connect some O's to it. And again, we're going to do this formally in just a second. Now, when you create bonds, when they are drawn right here, require electrons. And those bonds will count electrons out of the total that you did in step 1. So step 1 was to count. Step 2 is to connect the atoms using electrons from that count to make bonds. Step 3 is going to be with the remaining electrons that you have, you're going to put electrons around the outer atoms in your structure. Step 4 is to put the remaining electrons on the central atom. And then finally, step 5 is a cleanup step where if you don't have octets for everything, we're going to move electrons to make multiple bonds so that everyone has an octet. Now, because in the structure, or in the practice of drawing Lewis structures, because we want everything to have an octet, if at any point during these 5 steps you get an octet for all atoms, stop immediately and don't do the remaining steps. You're done. Okay? That could happen as early as step 3. Or even, I guess in like certain molecules, it could be step 2. So now what we're going to do is we're going to do CO2, and then we'll do a few other molecules for practice. So I'm going to put the steps back on the screen here. Let me hit clear. Then we'll go over to the previewer. I'm just going to put the rules up there for you. Alright, I got to zoom in so that I have space to work with. Alright, so the molecule that I'm going to choose to work with is CO2, like we said. And what we want to do is do these 5 steps in order. So step 1, count the valence electrons in all atoms. So I have a C, and then I have 2 O's. How many valence electrons is carbon contributing to the molecule? Well, look at the periodic table. Count the number of valence electrons that carbon has, and put that in your tally. So we know that carbon has 4 valence electrons for being in group 4. Each of these oxygens is in group 6A. It provides 6 electrons. And so in other words, what I end up having is I have a 4, and then I have 2 times 6. And the total number of electrons would be 6 times 2 is 12, plus 4 is 16. This means that when I draw CO2, I have 16 electrons to work with, because that is how many valence electrons it has. I can't use fewer than that because if I did, I would be leaving electrons out. And if I use more than that, then I don't have the right structure because I took too many electrons. I have to get it just right. You cannot use fewer or more than the number that you count. Now, if you make a math or counting mistake in this part, it's all over. Everything is wrong from that point. So this is actually the part that most people mess up, is they count accidentally, or they multiply 2 times 6 plus 4, and then they make an algebra error. Be really careful that you don't accidentally mess up your count, okay? Because it's very important. All right, so that was step 1, count the electrons. Let's do step 2. Step 2 is to draw the framework of my molecule. I want the atom that came first in the formula, that's the carbon, is going to go in the middle. And the outer atoms will be the other things that are connected to it. So I had O2, I'm going to put them on the outside, and now I got to connect them. Now every line that I draw is 2 electrons. Because remember, bonds are 2 electrons that are shared between atoms. So what that means is that I no longer have 16 electrons available. I took out 4, so now I have 12 electrons. And so that's our structure at step 2. For step 3, I need to reconfigure this thing. That'll work. So let me replace the structure that I just had. We'll do it in black because that was the old step. Step 3 is put electrons... There's a cat here. Hold on. Maya, go away. Put electrons around the atoms bonded to the central atom. So the outermost atoms get electrons. And what we're going to do is we're going to give them enough electrons, one atom at a time, so that each atom gets an octet, and then we move on to the next atom. And we keep doing that until we are done with the outer atoms, or we run out of electrons. So I'm going to do it like this. 1, 2, 3, 4, 5, 6. So in doing this, I put 6 electrons down. This line is the other 2, so this oxygen has an octet, so it is good. I use 6 dots to do that, so that means I have 6 electrons left because I had 12. Now I'm going to go over here and do the same thing to this oxygen. It has an octet. I used 1, 2, 3, 4, 5, 6 electrons. This line is 2 electrons. It has an octet. Uh-oh, we're out of electrons. But that's okay, we finished step 3. Step 3 was just to put electrons on the outer atoms. And we've done that, so everything is good. Step 4 is to put leftover electrons on the central atom. And so here's what our atom looks like right now. And if I had any electrons left over, I would put them right here on carbon. So I'd go dot, 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 but I don't have any. So if that's the case and we don't have anything available, we just move on to the next step. We tried to do it, but there were no leftover electrons. Step 5 is going to be to create multiple bonds. Oops, I didn't quite capture the screen. There we go. We're going to make multiple bonds to satisfy the octet rule for the central atom that needs electrons. So the way that we're going to do that is to zoom in really close, just to that's not at all what I wanted to do. Sorry, I hit the wrong button. That's about right, okay. What we're going to do is I'm going to take some of these electrons that are non-bonding, and we're going to make them bonding. So I'm going to say take these electrons right here, and I'm going to put them into a bond right there. So what that means is that these are going to go away, and this line will appear. When I do that, my structure will look like this. So here's the original, and here are the electrons that I didn't take. But these electrons now are in this bond. And if I check to see if I have an octet here, I have these 4 electrons, which should be 2 pairs of 2, but it just got a little sloppy. Let me make that look a bit better. And I have the wrong color. Hold on. There we go. That's a little better. So if I counted my valence electrons on this oxygen, I would say here are 4 of them. And then I have these 2 lines, which are shared for this oxygen. Each line is 2. So that's 4 total electrons. 4 plus 4 is 8. So this guy has an octet. This carbon, however, does not have an octet because we have not done the same treatment to the other side, which would be to take these electrons and put them here to make a bond. And now if we check octets for everything, the oxygen on the left had 8 because we just counted it. The oxygen on the right also has 8 because it is the mirror of the one on the left. And this carbon now in the center has 4 bonds connected to it. Each bond is 2 electrons. 4 times 2 is 8. Every atom has an octet. This Lewis structure is done. So this is the Lewis structure for CO2, following those 5 steps. Now that's a lot of information. So it's very important that you have the 5 steps handy and you go through them a few times. And then once you get the hang of it, you just do this process by memory. You don't even need the rules anymore. All right, so that's CO2. We're going to do another one in just a second. But I want everybody to be able to copy this down before it disappears. And hopefully oh, now it's gone. Never mind. Hopefully you got everything. All right, let me go back to the previous slide, put the rest of these on there. And I'm not going to refer to the rules, but I'm going to just kind of quickly go through it as we do this molecule. This molecule is CH2O. Oh no, there's 3 different elements now. What are we going to do? Well, we're going to follow the rules as written. So step 1, we're going to count the valence electrons. Carbon still has 4. Hydrogen still has 1, and there are 2 of them. Oxygen has 6. So I'll add them all together. 4 plus 2 is 6 plus 6 is 12. So I would have 12 electrons in this drawing. Next, we'll draw the framework. The atom that comes first, that is not hydrogen, is the central atom, so I draw C. I'm going to put everything around the outsides. Some of it is under the box because I'm terrible at this. Hold on. There you go. Sorry about that. I'll give you a second to catch up there. Sorry about that. Yeah, just yell at me if I make a mistake, because I might miss one message, but if I see a bunch of people just spamming the chat, it's on the left of my screen, and I will catch something, and then I'll realize, oh, I screwed up. I gotta fix this. But yeah, more messages gets my attention. Okay, so what are we doing? We're connecting. So we're gonna go boop, boop, boop. Everything is connected. I made 1, 2, 3 lines, so that's 6 electrons, for a total of 6 electrons left. Now I gotta do, I'll just put all the rules on the board. Now I gotta do step 3. Put electrons on the outermost atoms. Well, I got H here. How many electrons does hydrogen need? What do I gotta do to H here to satisfy its electron needs, we'll say? How many should it have? You type your answer in the chat. All right, all the 2s appearing. Hooray, it is 2. So, when you make a bond to hydrogen, it's done. You don't have to worry about hydrogens anymore. We gotta worry about this oxygen, though. It needs an octet. So I'm gonna go like this. 1, 2, 3, 4, 5, 6. The line is 8, so this one's done. And that used up 1, 2, 3, 4, 5, 6 of my electrons. All my electrons are counted for. Do I have an octet everywhere? No. I have to deal with this carbon. So again, no electrons to put on carbon for step 4. But step 5 is make multiple bonds, so I'm going to erase 2 of my electrons and add in a bond. This oxygen still has an octet. This carbon now has an octet. And there's the Lewis structure. All right. On the slides here, it's going to walk through how to do 6 CO2, but we just did this, so I'm going to scroll quickly through it. But what I want you to try and do is I want you to try and draw the Lewis structure for this molecule, NH3, ammonia. This is a pretty simple molecule. But just so that you have the practice of going through the steps, I want you to start at step 1, count all the electrons, then do step 2, step 3, step 4, step 5, etc., and keep going until you have drawn the correct structure and reach the end of the rules. So give it a shot, and when you're done, I will put the answer on the screen, and I have to be very... I kept talking even after I ended the mute. So what I want you to do is draw this Lewis structure, and we'll go over the answer when I get back. Sorry if I cut out there, because I hit mute and just kept talking. All right, how are we doing? Have we got the answer? Does anybody need more time, I should say, before I reveal the answer? If you do, type something in the chat and I'll wait for a second. All right. Survey says, ding ding. You should have a molecule that looks something like this. Now, if your angles are different, that's okay, as long as everything is connected the same. So if you drew your molecule kind of like, I don't know, something like this, and then just put the dots somewhere else, totally okay. What matters is that all the connections are correct. So hopefully you drew that correctly. That's how you draw Lewis structures. You follow the 5 steps, you make sure you do them in order every time, and you'll get the same answer every time too. All right, I'm going to put a bunch of molecules on the board for you, and what I want you to try and do is draw these Lewis structures with an interesting little caveat. On some of these, I put a charge. Now, if I have a positive charge on something, what do you think that does to your total number of valence electrons? Like, if you had a positive, what would happen to the number of electrons if you made something positive? Type it in the chat. Would it go up, go down, stay the same, explode? If you have a positive charge, the electron count goes down. Very good. So if you see something that's positive, you have less electrons, and you have this many less. So with ammonia, it's got a +1. What should I do with my electrons? Down here, I've got a negative. If I make something negatively charged, the opposite happens. It has more electrons. So these symbols will affect your step 1. When you're counting electrons, you got to accommodate for that charge. So go ahead and draw the Lewis structures for these. Pop any questions you have in the chat. I'm going to hit mute, give you a few minutes of silence to do this, and then we'll go over the answers in just a bit. My cat wanted to say hi. It sounds like people are in the middle problem, so I'll let you keep going. I'll hit mute again and check on you in a few more minutes. All right, hopefully most people are finishing up here. So what I want to do, I'm going to clear my canvas here. And I'll just draw so that it is there. Okay. All right, so let's do the 5-step plan for each of these. So CS2. If I count its valence electrons, it is, there are 2 of them. 2 sulfurs, so that's 2 times 6. Carbon is 4. That's 16. And what you'll notice is that as you do this structure, in every possible way, it resembles CO2. In fact, when I fill in the electrons like this, I hit the same issue that I did with CO2, and that is, oh, I have to move electrons around to make multiple bonds. So I did my connections, I put the electrons on the outside, and then I got to erase some electrons to make multiple bonds, and so this is what the answer looks like. So step 1 was to count it up, we got 16. Step 2 is to connect them all, which used, one line was 2, the other line was 2, so I guess I should actually keep this tally here for you. And then when I did the electrons around the outside, that used all the rest of them. And then I made the bonds in the middle, just like CO2. So that one we didn't really need to do much for. I already did CH2O. Oops. We can do ammonium, though. So I have 5 for nitrogen. Each hydrogen gives me 1. And then I have this guy right here, which we have to consider because it is minus an electron. So that means I have 8 valence electrons for this structure. So let's put our central atom. N is the central atom because it was listed first. I'm going to connect everything. And you'll notice that when you do that, you've used up all 8 electrons, and everything has an octet, and everything's happy. So this is the structure that you want. But there is one last thing that we didn't mention, and that is if you have an ion on your formula when it's written like this, up at the top here, you also have to put it on your Lewis structure. And so the way that we do that is you put square brackets and you put it over here. Mostly because I don't know where it should go. Should it go on the end? Should it go on one of these H's? Where should it go? Who knows? Right now, we don't really know yet. But we'll learn a little bit more about that later on today. For now, you just put it in the top corner. And so this is just convention for any compound that has a charge. You gotta put the whole thing in square brackets and put a charge up in the corner there. For PCl3, I have each phosphorus is 5 because it's in group 5A. Each chlorine is 7 because it's in group 7A. I have 3 of them. 7 times 3 is 21, plus 5 is 26. I didn't cover it today. Okay. The central atom is the one that's listed first, so we'll do that. Connect, connect, connect. I made 3 connections, so that's 3 bonds times 2 electrons per bond is 6 electrons. 26 minus 6 is 20. Now I'm going to put electrons on the outside. 1, 2, 3, 4, 5, 6. That one's done. 7, 8, 9, 10, 11, 12. That one's done. 13, 14, 15, 16, 17, 18. That one's done. I did all my outside atoms, but I still have 2 electrons left. Well, that's where step 4 comes in. Put them on the central atom last. There they go. Has an octet. Everyone has an octet. It's done. So this is what PCl3 should look like. And then finally for ClO minus, that should be a minus there. Instead of a minus, that was just terrible. Let me try that again. Oops, there you go. So chlorine is 7, oxygen is 6. What do I do with this negative charge? I add 1. Now, there really isn't a central atom when you only have 2, so all you have to do is just connect them. And then when you get to the next step, so that cost me 2, which is put electrons on the outermost atom first, I would just pick the one that we would normally have said was an outer atom. So we'll start over here, because it was the element that was listed second. Remember that the first element would be our central atom. So that was 6. And you're going to see that it doesn't really matter which direction we went, because everything has got an octet. Just got to put my brackets and put a charge in the corner. That's all there is to it. Alright, so hopefully you got those for your Lewis structures. There's the one up there. I didn't do CH2O because we did it earlier. Are there any questions about drawing Lewis structures? Because that's it. That's all there is to it. There is the homework practice. And so we will want to do as many of those as we can, because this skill will be crucial in what we're going to do for the next sections. All right. In Chapter 4, we talked about polyatomic ions. You can draw Lewis structures of these too, and we're going to do that for some more practice. We have already drawn a few polyatomic ions. I believe that this slide is going to show how to draw them for cations and anions. You don't really have to worry about the metals in these because they will not really have a structure. And we already discussed that if you have a positive charge on something, you have fewer electrons, whereas a negative charge gives you more electrons. So what I want you to do, and let me just go straight to these examples here, is in these polyatomic ions, what I want you to do is ignore the metals. So ignore this guy, and ignore this guy. And I'm just going to put the charges on here from your list of polyatomic ions. And some of them don't actually have charges. So I want you to try and draw these additional atoms here. Or not atoms, I'm sorry, molecules. Draw their Lewis structure. Now for all of these, you should have a central atom. Even N3, one of the ends will just go in the middle. Don't loop them around in like a circle or a triangle, because you'll get the wrong answer. That's why. Go ahead and draw these, and we'll go over the answers in just a bit. How are we all doing? Any questions? Any questions at all? Let me know in the chat. All right, let's go over the answers to these. We'll do, oops. There we go. All right, so just like before, we follow the exact same 5-step plan. So nitrogen has 5, oxygen has 7, and there are 3 of them. And this minus sign means that I add an additional electron. So the total number of electrons here should be 21. I messed up. That's my problem. I was like, wait a second, I shouldn't get an odd number. There you go. I bet everyone's furiously typing in the chat. It's not 7, it's 6. Yeah, it's 6. It's totally 6. Oxygen is 6, 18, 23, 24. There we go. That looks better. All right, that was step 1, count your electrons. Step 2, create a skeleton framework. 2, 4, 6. Step 3, put the electrons around the outside. 9, 10, 11, 12. 13, 14, 15, 16, 17, 18. That was all my electrons. I don't have any left to put on the N in the middle, but I can make a double bond. And since it doesn't matter which one I pick, I'm going to just pick the top one. I could have picked this one, and it would have been the same, because then I could just rotate the whole thing around, right? So whichever orientation you pick, that's good enough. There you go. Oh, and because it's an ion, we got to put brackets around it. So let's do that. There we are. All right, let's do the same thing for carbonate here. Carbon has 4, oxygen has 6. There are 3 of them. And then this -2 guy right here is 2 additional electrons, 18, 22, 24. Oh, that's interesting. That's the same number of electrons that we had over here. I wonder if they're going to look the same. Let's see. So there went 6, so now I have 18. Yeah, that's just like last time. (13, 14, 15, 16, 17, 18). And then I got to make a pair, turn into a bond. And then I do this, and it's all done. So 2 minus for the charge. And you're all set. So it turns out that molecules that have the same number of electrons will have very similar structures if they have the same number of atoms. And there's many ways that this can come about. But the only real way to get the correct structure every time is to count the valence electrons and then follow a 5-step plan. For N3-, there are 3 nitrogens, and I have this extra electron from the minus charge, so that's 16. I don't know why my equals is way down there. All right, who's the central atom? Could it be nitrogen? I bet it is. So I'm going to do this. That cost me 4 electrons, so I have 12 left. 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. This is looking an awful lot like CO2, isn't it? And in fact, when I do this and this, I get that as my structure. And there you go. And then finally for CN, I'm just going to draw the answer for CN really quickly. CN looks like this. And there's the result. Just because we're getting up to the break, and I want to let you guys take a break. We've been drawing Lewis structures for an hour. And we're going to draw more of them when we come back. So let me put the title card up. That's not the title card. There's the title card. Boop, boop. I don't have a timer, do I? No, hold on. There we go. All right. So please enjoy a 10-minute break. I'll start the timer now. And then I will see you for that when the 10 minutes are up. See you in a bit. I was close. I almost got it. Alright, where are we? Oh, we're going to do geometry. Okay. So, if you did the Lewis structure section just now and you thought, man, I need more practice at this. Well, guess what? We're going to do more practice in the geometry section. Because what we're going to talk about here is how do molecules exist in 3D? And once we have discussed that in a little bit of detail, then we'll have a general way to envision what we are writing on the paper and how it actually exists. And that could help a lot, because drawing these structures at first, it's just kind of like, okay, I'm doing this, but what does it mean? And we're sort of just taking it on faith that, like, oh, okay, this is in the middle and there's stuff connected to it, but what exactly does that represent? All right. So on the screen here, you can see a little picture of a model kit. If we were in the classroom, I would be going upstairs to the laboratory to bring down the model kit so that you could build things and have something like you could actually manipulate. Unfortunately, we don't really have that option. So for this week's lab lecture, what we're going to do tomorrow is I'm going to give you a worksheet that's just full of these. And you're going to draw Lewis structures until your fingers bleed, and your eyes fall out, and your hair, I don't know, whatever hair does when you're exhausted. You're going to draw lots of Lewis structures. And the whole point of it is to become proficient with it, and then explain their geometry. But when you draw stuff on your paper, the only way you can do that is to draw it flat, because we don't have a three-dimensional way to draw. I mean, not easily, I should say. You can get that Google thing where you wear goggles and you can paint in 3D, but that's not going to help you so much at this time. Not as much as baldness, that's right. I thought about shaving all my hair off because it's just going to keep growing, and I don't know how long this whole quarantine is going. And I don't know if I can stand my hair getting any longer. Anyway, drawing structures on paper is a little bit misleading because the paper is flat, the molecules are flat, everything is flat, and things in reality are not two-dimensional. For example, if I turn sideways, I don't suddenly disappear like Paper Mario or something. Molecules all exist in 3 dimensions, and just like all matter that is made of molecules, that must be the obvious consequence. So what we need to do is we need to study how molecules can exist in 3D by devising some sort of scheme to describe them. And so the way that we're going to do that is first we're going to draw the Lewis structure or something. And when we draw the Lewis structure, we will then make predictions based on what we drew. So this does require us to make the Lewis structure correctly. Once we have done that, we can then predict its geometry. And so here's how that's going to work. So let's take a molecule, any molecule like this. I'm going to just use CH4 for a lot of this because it's a very simple molecule. And I'm going to ask myself a question. Well, first of all, I'm going to ask a pre-question. And that is, where are the electrons in CH4 located? And so, when I say electrons, I mean just the valence electrons. Those are the electrons that are involved in the construction of the molecule. And hopefully you would say, well, they're right here in these bonds. As shown. Now, if I drew another molecule, say water. Water is H2O. And that looks like this. And I asked you, where are the electrons in water? You could say, well, there's still the bonds. But there are also these pairs of electrons here. Everything is all electrons in this structure. Okay, well, with that consideration, where are the electrons around the atom if the electrons take up space? And unfortunately, I have to erase one of my structures here because you can't see all of the text here. Now, electrons take up space because, even though they're tiny, they have a negative charge. And the negative charge on electrons causes them to repel other electrons. Now, if electrons are paired together, they're stuck together and they're happy enough. They still repel, but not as strongly as they would repel other neighbors. So what that means is that if I were to assign each of these arrows that I drew earlier a letter, I'd say A, B, C, and then D. What that means is that A will repel from all of the other things, B, C, and D. B will repel from all the other things. And so on and so forth. Everything is pushing apart as far as it possibly can, because these sets of electrons do not want to interact with each other. So what I have drawn here on these A, B, C, and D things, here, let me get D in here too. These are what are called electron groups. And electron groups are just things that have electrons in them. That can either be a bond, and that could be any number of bonds. So single, double, or triple. Those are all an electron group, because there would be electrons in that spot. The other thing that electron groups could be would be a non-bonding pair. So whether I have a line or a pair of dots, I'm going to count that as an electron group. If I have 3 lines and they're all on top of each other, that counts as an electron group too. All we care about are where around the molecule are my electrons located. Can I find spaces that have electrons in them? Those are our electron groups. All right. And so the text that will pop up will actually describe that right there. We're going to do that in a little more detail on this next slide. But this is the premise for how we determine the geometry of molecules. And this is called VSEPR theory, or Valence shell electron pair repulsion theory. You might ask, that's a lot of word salad. What does that mean? Well, let's go through the words one at a time, and we'll get a different color as we do this. Do orange here. So what does valence shell mean? Well, the valence shell is where electrons on the outside interact with other atoms, right? Anything that's on the outermost layer of electrons is considered to be valence electrons. Electron pair, what does that mean? Well, so far we've seen that all of our electrons like to pair into sets of 2, right? A bond is 2. 2 dots on one side of an atom is 2. So electrons must be in pairs. Repulsion, what do electrons do? Well, they repel each other. And then theory just means, oh, this is why all of this happens. Now again, remember, we are going to count these bonds and these non-bonding pairs each as one electron group. And again, bonds could be single, double, or triple. And as long as they are in the same space, we're going to count any of those, single, double, or triple, as one electron group. So our task is going to be, we're going to draw the Lewis structure of a molecule, and then I'm going to look at the central atom, and I'm going to count these electron groups. And there it is, VSEPR electron groups. Depending on how many electron groups we have, that's going to dictate what the geometry of our molecule is. So let's do an example by going back to some of the molecules that we drew before, because I haven't erased them yet. And you're going to notice that the molecules that look the same have the same number of electron groups, and that's not a coincidence. So here's our NO3 that we drew earlier. And I realize that this isn't super useful to us. That's okay. But if I look at this, this is my central atom, and I say how many electron groups are around the center atom. So what I mean by that is only stuff that's connected directly to it. And so that would be this bond, this pair of bonds, and this bond right here. Now, because this pair of bonds is in the same space, they're both connecting these two atoms together, I'm going to count it as 1. And so what I would say is I have 3 electron groups for this molecule. If I go over to CO3, then I would count them the same way. So here's a group, here's a group, here's a group. 3 electron groups. Now you'll notice that they both kind of have the same shape. They look kind of like a triangle, right? Let's go down here. Let's count electron groups on these two, which also look kind of the same. I'm going to pick this as my central atom because it's in the middle. And then count all the groups that are connected to this central atom. This is a group, and this is a group. So I'm going to say 2 electron groups. Same thing over here. I'm going to pick this as my central atom just because I could pick either one. It doesn't matter. This is still a group, but this is a group too. And so that's why these shapes look pretty similar. This one's just over on the left here. This one's just a little longer. Let's do some more examples here to count electron groups. I'm going to give you these 2 molecules real quick. So what I want you to do is draw the Lewis structure of these molecules. So we'll do CF4, and then I want you to do PCl We already did PCl, didn't we? I mean, this is enough to drive people to drink, so we're going to do PBr. And I'll even let you have 3 of them. So, draw PBr3 and CF4. Draw their Lewis structure. I'll give you a few minutes to do that. And then once you've done that, I will draw the Lewis structure too. And we'll talk about how many electron groups it has. But once you have drawn it, try and count the electron groups around the central atom yourself and see if you notice anything similar about them. So go ahead and try it, and we'll be back in just a second to go over the answer. All right, how are we doing? How do we do on CF4 and PBr3? I'm going to show you just the answer here for these structures. And if you need me to, I can walk you through it. So post in the chat if you want to see how I got this answer. And we'll do the 5-step plan if you need to. All right, so there's CF4. And then PBr3 would look like this. And again, if you want to see these steps, let me know in the chat. Oh, my cursor is in the way. Let me move him out of there. All right. So if I'm going to count the number of electron groups on each of these molecules, I first select the central atom. And then I would indicate any of the regions around the central atom where electrons live. So that would be here, 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 and here. So this would have 4 electron groups. And the same thing with this molecule over here. My phosphorus is in the middle, and I would circle these 3 as my groups, but I also have this pair on the central atom, and so it also has 4 electron groups. And there you go. So that is how we count electron groups around a central atom after we have drawn the Lewis structure. Now, each of these numbers, so we've got 2, 3, and 4, you can see the shape is different, but between the two, it's sort of the same. Here, I just have the 4th direction points up, and there's just electrons there. Whereas here, the 4th direction points to an atom. But the general gist is pretty similar. Whereas if I compared this one with this one up here, it's very different. Like, there just isn't anything in the up and down direction. It's completely blank. So we're going to use these different families, this 2 electron group, this 3 electron group, and then down here the 4 electron group, as our templates. And yeah, so we only ever count the central atom. So anything that's going on the outside, we don't care. So over here on this molecule right here, we're going to ignore the outer atoms when we count the electron groups. We only care about the bonds to them, because the geometry is going to be dictated by what's in the center. And the reason for that is because if I draw my molecule like a space-filling model like this, so here's my central atom, and I have something going up, and then something going this way, and then something going this way. If this guy has electrons on it, it doesn't really matter because it doesn't affect the geometry. All right. So here are some cartoon diagrams of the molecules that I drew, and you'll notice that one of them is actually a little different than what we did on paper. And this is actually a sort of just failing of paper. It only exists in 2 dimensions. The other ones we did pretty good. So for example, here was the one where I had nitrogen like that. I could just draw over these. So there we go. We could say, oh, here's one electron group, and here's the other electron group. I could do CO3 2 minus. I drew an extra dot. I didn't mean to. Boop, there it goes. And then over here, I could either do CCl4 or I could do PCl4. It doesn't really matter. I'm going to do the P one. So PBr, BR, BR. And then for this last one, well, I had a pair of electrons here. And that was it. And so all of the things that I circled as groups went along these connectors, because the connectors are where my electrons live. Now, interestingly, for 4, so 2 and 3 we did, and that looks pretty good. But for 4, we ended up making a tetrahedral shape. So what I should have done on the previous slide is, if I was drawing these correctly for geometry, I would get something that was different than a box. And what we're going to do is we're going to explain why that is. So let's go back to this page here. What I'm going to do is I'm going to delete... Oh, that's not delete. I'm going to delete... That's also not delete. Why is this a thing? Or you know what I can't do? I'll just... Whee! There, it's gone now. I made some space. Where did it go? I don't know. It's not my problem. Okay. I'm going to take this molecule, CF4, and I'm going to try and draw it like a tetrahedron. And I've already drawn the Lewis structure above, so I know the connectivity. But what I'm going to try and do is I'm going to try and draw it the best that I can to represent its three-dimensional structure. And we have a guide to guide us here. Sorry, I put the pen in my mouth, so... Alright, so this is what my structure should look like. We'll just stick it right next to it. There you go. In fact, even what I can do is I can do this. Can we see the resemblance? Hopefully you can. So this is the proper way to draw a molecule with 4 electron groups. And now we have to answer the question, why? Why do I have to do all of this work? Why can't I just draw it like a square? Or why doesn't it exist as a square? That is also a good question. Going up to this structure up here, if I asked you what the angle was between these electrons and these groups, and you had to go back to your geometry days and give that a number, how many degrees are between those two bonds? Type it in the chat. Let's see if you know. Give you a hint. It has to be a right angle. Because we drew it like 2 intersecting lines, basically. The up-down line and the left-right line. How many degrees? Oh, no geometry fans, huh? Oh, there we go. The answers are coming in now. 90 degrees is correct. All right. So this diagram, if I drew everything just like where my atoms were at right angles like this would be 90 degrees. Now, looking at how I've drawn this down here, what do these angles look like they are to you? Do they look like they're 90 degrees, or are they more, or are they less? And you have the 3D structure to look at too, right here. So look at this 3D structure and tell me if you think that that angle is more than 90 or less than 90. You don't have to tell me the number, because I don't know if you could calculate it from just looking at the picture. And that's correct, yeah, so it's definitely got more. It turns out that this angle is actually 109.5 degrees, which is not a number that you need to memorize. But what's important is that this number is bigger than this number. And what did we say that electrons do? Well, they repel from each other, right? So if you had the option of being 90 degrees apart from something else, or 109.5 degrees apart from something else, and you really, really hated that something else, you would always choose the option that gets you further away. So whenever we look at a molecule that has 4 groups around it, we always draw it like a tetrahedron. And so we'll never draw it like this. So we're never going to draw molecules in this square sort of shape ever again. It was okay to do it before, but now we know better. So that's where the tetrahedral arrangement comes from in our molecules. So now we have an extra consideration when we're drawing a Lewis structure. You could draw the Lewis structure just however you want, then count the electron groups, and then you have to make it match one of these default shapes. Because these 3 shapes are the shapes that molecules exist in. Now, there are more shapes than this. You can actually go to n equals 5 and n equals 6. We don't cover them in this class because they use more complex electron structure. For example, we break the octet rule doing that. But for our purposes, that will be okay for this course. All right. In all of these diagrams, the pink sphere is the central atom, and the white spheres are whatever the electron group is connected to. So these connectors are our electron groups. And if it's an atom, you would put the atom in this space. And if it's a pair of electrons, it would just go in like the little white stub right there instead of in the space. But it's generally the same area, so you treat it however you really want to. So 1, 2, 3 here, and then 1, 2, 3, 4. Now these names are associated with these groups. So if we go back to our sample problem right here, and this is not going to be useful to us, so we'll just hide it. Boop, we'll just do that. Now what we can do is we can assign these molecules shapes. So we'll go back up here. I have 2 electron groups on this molecule, so if I wanted to give it a name for its shape, what would the name be that you would call it? What should I call N3 minus? What is its shape? Very good. Yeah, it's linear. And so if I say that this is a linear shape, you would just say, oh, okay, all the atoms are in a line. Same thing over here. This one's linear too. And the reason it's linear is because it has 2 electron groups. Well, what do I call something with 3 electron groups? Oh, it slid off the table. That's okay. What do I call 3 electron groups? Can I bring it back? Oh, it's still there. So 3 electron groups would be what? Trigonal. Now, specifically trigonal planar, because we're going to introduce a second trigonal in a second here. And there you go. So that is the basic geometry of these molecules. Now, the next thing that we're going to do is we're going to try and determine the shape of a molecule if we consider all of the electron groups, but then we omit the spaces where we have only electron pairs, because an electron pair is really tiny. So for example, if this was an atom and this was an atom and this was an atom, but this was an electron pair, then none of this would be visible because this atom isn't actually here. And so our shape, instead of being like this, where I had like a tetrahedron, it would instead be more like this, with my electrons on the top. Oh, damn it. Okay, hold on. Let me erase. We'll go back to the slides. Let's actually show you what I'm talking about here. So what we're going to consider now is when we have both atoms present and electron pairs. So I'm going to put electron pairs right there for those. Because if I had all four of them as atoms, this is the shape that I would get. I would have... So this would be my top atom. Here would be my side atoms. And then the central atom is in the middle here. That would be the shape. It'd be a tetrahedron like this. But if this atom is an electron pair and this doesn't exist because it's just a pair of electrons, the new shape that I have is now this. And so you can see that these two shapes are similar, but this guy is squished a little bit more because there isn't a top part of the molecule. That's just an electron pair. So if we add electron pairs to the mix, we got to consider how the shapes change. And so we'll do that on the next slide. So what we're going to do is we're going to consider each family. The three families are what we just considered: linear, trigonal planar, and tetrahedral. And then what we're going to do is we're going to substitute out atoms for electron pairs and see how the shape changes. If the shape changes appreciably, we're going to give it a new name. And that name's going to be the molecular geometry. So for every atom, or I'm sorry, every molecule that we're going to draw the Lewis structure for, we're going to give two geometries. We're going to give the VSEPR geometry. And that's going to be what family of shapes the molecule belongs to. And then we're going to do the molecular geometry. And that's going to be a mess because I can't draw the letter M, apparently. Molecular geometry. And that's going to represent which member of the above family. Now, in your textbook, there is a giant chart. And I also have a website link that I'm going to post in the chat real quick. The issue with this link is that it does require Java. So I want to do this and copy this link. And it will ask you to either download or run something, and it will require you to do that. So here's the link to this. But this is a really useful simulation. And I actually have the simulation in the miscellaneous tab. I don't know if I've revealed it yet. But before we actually play around with that, and you can click on it and play around with it if you want to, while I'm describing the shapes, I'm going to go back to this slide. Or back over here. And what we're going to do is we are going to draw all of the different possible combinations of all the shapes that we're going to do in this class. And there aren't actually that many. All right. These two columns we have already done. If we had something that had two electron groups, then what we said was, okay, here's my central atom, here's the first thing, here's the second thing. I'm going to call it linear. Let me try and get the column name up there again. If I have three groups, then here's my central atom. 1, 2, 3. And I'm going to call it trigonal planar. And then finally, if I have 4, central atom, top one, and then I got the 3 bottom ones that look kind of like the base, that's tetrahedral. All right, new color. That's the zoom function. I don't want that. Let's do dark purple. All right. What we're going to do now is I'm going to make a new column. And that should say number of electron pairs. And so what this will say is that of the two electron groups, how many are electron pairs? Well, if there's 0, the molecule looks the same because both of them must have been bonds. If there was 1, then the molecule would look like this. Here's my bonded one, but then the other one is an electron pair. The name that we're going to give each of these is going to be called the molecular geometry. And in some cases, it's going to make our molecule look drastically different. And in other cases, it's going to look more or less the same, and we're just going to call it the same name. In both of these cases, everything is still in a line, so we're just going to keep calling it linear. So when I ask you to name a molecule that falls into this category, you're going to say its VSEPR geometry is linear, and its molecular geometry is linear, because there are 2 electron groups, and whether 0 or 1 of them are electron pairs, it's still going to look like a line. Down here for 3 is when things get different. If I have no electron pairs, then everything looks the same, and I call it the same thing. But if I have 1 electron pair, I'm going to just chop this top part off here. So there's my electron pair. Now it doesn't look like a triangle at all, because I chopped the top off. I lopped its head off, right? In fact, it looks kind of more like linear, except for a problem. It's not in a straight line. It's kind of got this bent line thing going on. And in fact, that's the name that chemists came up for it. They couldn't figure out anything better, so they called it bent. I think your textbook also calls it angular, but that's more syllables, so... Now, if I took off this second one right here, I would end up with something that looks exactly like up here with extra electron pairs. And that'd be linear, so we're not even going to bother with that. Down here for 4 with tetrahedral, 0 is going to look exactly the same as our template. So we'll call it the same as our template. But 1 is going to look different. I'm going to lop the top off right here. So now I have something that just looks like my little squished pyramid here. And I'm going to draw my squished pyramid here. There we go. Versus my tetrahedron, which would actually be a much taller one. Oops. So these are not the same thing. This one is much shorter, so we're going to give it a different name. We're going to call it Trigonal Pyramidal. I didn't put the electron pair on here. I'm sorry. There we go. Oh, I got it just before you asked me. I forgot to put the dot pair. And then for the second option, if I want to trim out a second one, I'm going to take this one in the front here. So that means that I still have the electron pair on the top. I still have this guy going in the back, and I still have this guy kind of coming in the front. And now I have another pair of electrons right here. Again, this looks kind of like linear, except it's not linear. So we're just going to call it bent because it's a bent line. I'm going to put all the names in boxes here. If this was an in-person class, we would be memorizing all of these names. and how to get to them. But since we're online, you just look at this table that you have drawn, hopefully. Ah! I clicked off of my screen. That's why I quack like a duck. Wah! What happened? All right. I think what I can do is I can zoom this out a little bit so that we can put the whole table on the screen here. There we go. So that's what it looks like. Again, when you are asked to do this for a problem, you are going to choose a name from this column, and you are also going to choose a name from this column to describe your molecule. Okay? All right. So hopefully you have all that handy, because we're going to do a bunch of examples. On page 130 of your textbook, and I believe this is if you have the most recent edition, is this table that we just made. Okay, so you can refer to this table from your textbook, or you can use this. There will also be one in the lab that I'm writing up tonight. I'm going to put that in there too. You'll have this available, and you'll want it for the exam so that you can answer the questions. But let's talk about what we need to do in order to answer questions and then assign names. So step one, just like we've been advertising all along, draw the Lewis structure of your molecule. You've got to make sure you do it right. Step two, you're going to determine what family the molecule belongs to by counting the number of electron groups. It says electron domains there. I just realized that is... So domains is just something that is used in a different textbook. It's the same thing. You're going to count the number of electron groups to determine the VSEPR geometry. So that's this. The family of the molecule is the VSEPR geometry. And then you're going to count how many of them are non-bonding pairs, and that's going to be the molecular geometry. So let's do some examples of this. And then we'll refer to the chart. So I want to know the molecular geometry for ammonia. So be careful, because the terminology here is really what's going to get you. Which of these is the molecular geometry? I want this one as my answer. On Canvas, I can really only ask you one question at a time. And so I might ask you a question that says, what is the VSEPR electron geometry for your molecule? That might be a different answer than your molecular geometry. So be really mindful that the question you see on the screen is the question you're answering. And try not to jump to a conclusion like, oh, I know how to do this, and then I actually asked you to do something different. So I'm going to draw the Lewis structure for ammonia. And just like before, we could count valence electrons. So 5 plus 3 times 1 is 8 electrons. I'm going to try and draw this as accurately as I can, remembering that something with X number of groups around it generates whatever shape. But I might not know that at the start, so we'll just do this to start. I don't know, this seems like a good guess. Maybe it's trigonal planar. Doing this cost me 6 electrons, so I still have 2 left, which means I had to put 2 more down. Uh-oh, so my structure isn't really that good. This doesn't show the 4 electron groups very effectively. So what I'm going to do is I'm going to redraw it. I'm going to try and draw it so that I show the 4 electron groups more effectively. There we go. That looks pretty good. So our Lewis structure is set. Now what I need to do is count the number of electron groups. How many electron groups are around the central atom? Just like before, we count where are the regions that there are electrons that are touching the nitrogen here. So that's this guy, that's 1. Here's 2. Here's 3. And then my pair of electrons is 4. So I have 4 electron groups, which means that the VSEPR geometry is tetrahedral. And we get that answer by going back to this table that we just made. Let me turn this guy on real quick so that we can get our answer here. Sorry, I'm going to cover up the table real quick. There we go. So I had 4 electron groups. I'm pointing at the screen as if you can see me. Oops, that's not what I wanted to minimize. There we go. I have 4 electron groups. So the VSEPR geometry shape name is tetrahedral. Now I got to figure out how many of those are electron pairs. Well, in the diagram that we drew up in the corner up here, which I can't get to because it's in a different window, but it's up here. How many of the electron groups are electron pairs? And what should I call this molecule for its molecular geometry? Type your answer in the chat. I'll leave this on screen for just a second, and then we'll go over the answer. Together. What molecular geometry do you want to give it? So there's 1 pair of electrons. That's correct. So 1 pair of electrons. So the molecular geometry is going to be called, and I have no idea if this is fitting in the box, just barely, Trigonal Pyramidal. And that is way too tiny and you can't see it, but that is the right answer. So let's do that. I'll just make it bigger. And that's how you determine the geometry of a shape. Step 1, draw the Lewis structure. Step 2, give it a VSEPR geometry. So that's going to be something in this left column here. Right here. And then step 3, count the number of electron pairs. That will give it a name for something in the right column. Now keep in mind that these are sort of subdivided into these regions. So I can't have something that is bent but also linear. That's not possible. Okay? Linear only applies to things with 2 groups. Bent would be 3 or 4. Those are in different families, so you can't choose those 2 answers together. So on your exam, don't say something has a linear VSEPR geometry and then a bent molecular geometry, because I'll go, oh, they didn't understand the chart. That's no good. But that's how you do it. Draw the Lewis structure. Figure out what family it's in by figuring out the total number of electron groups. And then consider electron pairs to get the molecular geometry. All right. So I'm going to hit clear on here. We're actually out of time today. I went over by like 8 minutes here. But let me hit clear on this slide. We'll go back to here. What I want you to try and do is draw the Lewis structure for CO2, or find it in your notes where you have found CO2 and drawn it. Count how many electron groups it has, how many electron pairs are around that central atom, and then quickly give it a molecular geometry and type it in the chat. And you should be able to identify that one pretty quickly because, spoilers, there's only one answer for it. It is indeed linear. Very good. And the reason that it's linear is because there are 2 electron groups on CO2, the double bonds coming out of the C. And of those 2 electron groups, none of them are electron pairs. All right, that's molecular geometry. So I have the homework practice problems for you here. You're going to notice something really weird about this one. What is this metal doing in here? Is it possible that metals can do covalent compounds too? And the answer is, yeah, there is a gray area. Things can do more or less whatever they want to in the middle. So treat this molecule as if it was some sort of like polyatomic ion that still made covalent bonds, because it actually does. So for your practice between today and tomorrow and Thursday, because we're going to do more of this tomorrow because that's the lab lecture, I want you to draw these Lewis structures, and then I want you to identify their VSEPR geometry, and then their molecular geometry, and we'll make this the first thing we go over on Thursday's lecture. If you're around tomorrow too, we can also go over additional ones that you might do in the textbook, because there's a whole bunch of these. But being able to identify geometry is one of the core features of this class. And so if you can make it here, then a lot of the stuff that we're going to do will be much, much easier. And it takes time. Like, this is not easy. So if you are stuck tonight, you're like, man, I feel like I need a lot more practice, then that's totally fine. You're not going to become an expert at this because you drew 4 Lewis structures. You might have to draw 400. Well, fortunately, there's a lot in the textbook, and I have an assignment for you coming up. So you'll get some practice, and if you're still struggling after that, then we can keep working on it in another way. But for now, I do want everybody to try and do these in as many as you can. I'll see you tomorrow for the lab lecture. Let's put the title card back up. Oops, we're not on a break. I can get rid of that. Thanks for coming out. Have a wonderful evening. Stay healthy, stay happy, and stay at home.